First topic we're going to get into is peak pressure. And peak pressure is the big change that's occurred in the 2012 version of NFPA. Actually, the requirements for peak pressure evaluation came out in 2008, but the standard was a bit of a jumbled mess, and I don't think anybody could make heads or tails of it. So we kind of look at the 2012 version as the official one that says, yes, you've got to start doing a peak pressure evaluation. So that's what we're going to be start talking about a little bit today. Anyway, everyone's quite familiar with peak pressure when it comes to inerts, and of course here's a little peak pressure spike that we get when we have, say, an argonite or any inert agent discharge. The big surprise came that we can get similar but different looking pressure spikes when we're dealing with halocarbons. Now, if we discharge an inert agent and a halocarbon into the same enclosure, yes, the inert agent will produce a lot more peak pressure. But since we have to make the enclosure quite a bit tighter for the halocarbon, the peak pressures can often be roughly about the same, maybe a little bit more for the inert agents, but in some cases the halocarbons, in some instances the halocarbons can actually produce more peak pressure than inerts. And what's interesting about it is they can produce peak pressure in both directions. And often the negative peak pressure direction is larger than the positive peak pressure direction. But that's part of the evaluation, and the evaluation will tell you what the size of the negative and positive peak pressure spike will be. So these peak pressures are all pretty much a function of the enclosure leakage. As the enclosure leakage doubles, the peak pressure more or less doubles, and it varies with the different agents. It's not a linear relationship. It's an odd power relationship, and each one of the agents has a different peak pressure formula. The easy way that we discovered to compare one agent to another is to look at the leak to volume ratio of the enclosure. So if everything is the same and we double the size of the enclosure, the peak pressure stays the same. So as long as if the enclosure leakage doubles and the enclosure volume doubles, then everything is the same in terms of peak pressure. So it doesn't really matter so much where the holes are in terms of peak pressure development, but it is very dependent on the leak to volume ratio. Unless you're dealing with very, very small enclosures where the walls have a big effect, but most of our enclosures are much bigger than that, so really it's the leak to volume ratio that affects it. And with halocarbons, we also have to take humidity into account, and we can see here that as the relative humidity gets greater, then the negative peak pressure drops. That's the red line here. So when we get up to, say, a 70% relative humidity, the negative pressure spike pretty much is eliminated. And they tend to be the same at around about 40% or so. And the reason for that is that when the air is saturated, there's very little, I guess, flashing. The flashing from liquid to gas is slowed down, and the cooling effect is slowed down, and it's this cooling effect is what produces the negative pressure. As far as inerts are concerned, we can ignore the effective humidity. There basically isn't much of one. So there's a few things that we have to look at when we're talking about peak pressure design. The first one is we have to specify the enclosure strength, which is sometimes a big mystery. But we do have a table that I believe I have in the presentation that has some appropriate values, and a typical 2x4 wall will take around about 250 pascals or 5 pounds per square foot, and a well-constructed 2x6 wall with sheetrock on both sides and pinned at the top and bottom, meaning that it's not a free-floating wall. It's attached to the slab above and slab below, will quite easily handle 500 pascals, and we've had these walls up to 1,000 without too much of a problem. So that would be the first thing, is to specify the enclosure strength, which has to be part of the specification. And once we know that, we can determine the necessary leak to volume ratio. And I'll just quickly jump over to our new software, pull it over onto the screen here, and I think you can see that. And this is our venting calculator. So we'll just start up the venting calculator. And as you can see, we're just going to do this in mixed units here. So here we have to put in the venting equation that we're using, in this case FSSA for NFPA 2001, the enclosure leakage standard that we're using, discharge type, in this case let's call it descending interface, and let's say we've got argon or argonite, pretty much works the same way, 40% concentration, 60-second discharge time, temperature discharge, put in the volume of the enclosure, the maximum flooded height, and so on. And then when we hit calculate, it will tell us, based on the parameters that we've put in there, what the peak pressure will be. In this case, the enclosure pressure limit is 500 pascals, and we're going to require a PRV of around about 2,000 square inches. If we were to change this, for example, to 1,000 pascals, you'll notice that the PRV size reduces. If we were to change that to 250 pascals, then the size of the PRV necessary increases. And as we change these parameters, for example, if we were to change the minimum protected height from 9.2 down to a more common, let's say 7.4 feet, and we recalculate again, and let's see here, our PRV requirement goes to 3857 square inches, but it also enables us to have a much leakier enclosure, and if we were to use enclosure leakage as part of the venting, it reduces the size of the venting. So this tool is designed specifically for the design of enclosures before the enclosure is even built, and you can compare different agents. For example, if we were to go to let's say FM200 and do a comparison there on the same enclosure, we can see that the PRV requirement is much more reduced. So we can go through the different agents, different scenarios, and check them out and find out what is required in terms of PRVs. Now, someone was saying it doesn't make sense that we would have a negative peak pressure. I guess that's why a lot of people, in fact, in most of Europe, install all vents as if they're positive pressure. There is an incredible amount of cooling that goes on when the discharge occurs, and the cooling is enough that it actually sucks air into the enclosure for about the first 4 or 5 seconds. It produces a very powerful negative pressure spike. And I can tell you that I've been there, I've seen the smoke going into the enclosure, I've measured the negative pressures personally. It's not something I've seen once or twice, I've seen it dozens and dozens of times, and it absolutely goes negative, no question. Okay, so we'll just set that aside for the time being. So as far as the NFPA working plans, section 5.1.2.2, number 10 requires an estimate of the maximum peak pressure, and number 28 requires a specified pressure limit that we've talked about already, and Annex D1 also says the enclosure must be capable of withstanding peak pressure. So there's a number of places in the new version of the standard that requires some form of peak pressure evaluation, and if the enclosure can't withstand the peak pressure, then obviously you have to do something about it, which is to install pressure relief vents in many cases. Just a quick word on some of the manufacturer's venting formula. One of the things that we discovered is like the clock that's where the hands are stuck. It's right twice a day. The same thing is true with these equations. There is a point at which they cross over at around 1,000 or 2,000 pascals. So the dashed lines are manufacturer's equations. The yellow lines are the experimental data for inerts. And you'll see in the area of interest of 250 to 500 pascals and a leak to volume ratio which is typical of most enclosures in terms of retention time, that the existing equations that people are using are under predicting peak pressure by a factor of 1, 2, or even 4 times. So that means we're getting 4 times as much peak pressure as they think. So the new FSA formulas have been well vetted, and experimental data has been taken over a very wide range of pressures. Moreover, the data was taken in such a way that when you do a door fan test, you can actually use that door fan test data to properly predict the peak pressure. One of the missing links that we had before was when a peak pressure was measured, it didn't really relate to how we measure enclosure leakage. So the two weren't kind of in sync. And what I found out was most of the data was taken at the same leak to volume ratio, as if they did the same test over and over and over, and didn't take, the data was not taken over a wide range of enclosure leakage in order to find out what the shape of the curve is, which is why we have the curve shapes incorrect for most of the manufacturers. And they're slowly kind of catching on to this, and a lot of the, I would say pretty much all the major manufacturers in North America now have accepted the FSSA curves as being correct because they've been well documented against experimental data. So the important thing here is measuring the enclosure leakage in relation to how tight we're going to get the enclosures to pass the hold time. Because usually what will happen is we'll tighten up the enclosure so we get at least a 10-15 minute hold time. So that defines the leak to volume ratio in a way of the enclosure, which also defines the peak pressure. So there's a linkage between the hold time and peak pressure, and the new software shows you how that linkage works very well. And there it is there. We just took a look at the real software. It's the first tab on the software when you're running it. I'll just bring it up here for a second. Let's see. So this is what the software looks like, and there's various tabs on here as you can see, and we'll just collapse them all and so on. So the very first tab now is enclosure leakage design. So if we open up that, we get to do an enclosure leakage design initially. And then once we've done that and we're actually testing it, we can go through and put all of our test information in there and actually test the enclosure. But obviously in the enclosure design we're not testing anything at all, so this is just a theoretical what if we did this, what if we did that. So this enables you to test a whole lot of what ifs before the enclosure is designed to give you an idea of what you're getting yourself into in terms of inventing requirements. And there are some of the pressure relief vent manufacturers are now producing what are called dual acting pressure relief vents that will actually open in both directions. So they open going one way and they swing back and open in the other direction as well. So these would typically be, from an installation standpoint, more economical to install since you only have to install one vent. They're a little bit more expensive, but overall it's probably the best way to go. Let's see. So I'm not sure why I have this slide in here, except to talk about the confusion that we get with what's called dynamic discharge pressures and peak pressure. So there can be dynamic discharge pressures as a result of the velocity of the agent coming out of the nozzles, and in some cases hitting ceiling tiles and displacing them and so on. But there's also a pressure buildup there which can displace ceiling tiles and do damage due to the pressure impulse. So we've got both things going on in here. And also the other point here was that there is some agent that's lost during the discharge, but because we have cooling both with halocarbons and to a lesser degree with inerts, we have cooling as well. When the agent comes into the room, because cooling occurs, we don't have quite as much agent loss as we thought initially, because the decreased volume, I guess, of the agent that's being put into the room actually accommodates more agent. So what we discovered with most of the inerts is that almost all of the agent that is put into the room stays in the room, because during the entire discharge the pressure is going down, 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 and only when we get to the point where we have the nitrogen blowing down from the tank do we start to get a small positive pressure spike. What that causes is a situation where we have more agent in the room than we're supposed to. As that agent starts to warm up, it actually expands and supplies the leaks to some degree, which is the reason why we get much higher concentrations and much better retention times of halocarbons than we're supposed to, because we don't actually lose much of any in the way of gravity losses for the first 3 or 4 minutes, because the agent is expanding continuously. As it expands, it actually supplies the lower leaks, and we get very little air coming into the enclosure. As the agent warms up after about 4 or 5 minutes or so, we start getting to a point where the agent falls out the bottom and the air comes in the top. So NFPA is still using what we call the sharp descending interface. The interface, in fact, is not sharp. It actually, there's a zone in there which looks something like this, although not quite, where there's an air agent interface. This air agent interface is much narrower than the ISO equations predicted, and we came up with a new formula for that, which was called the thick interface, and that's been accepted by ISO. What it amounts to for the halocarbons and NFPA, the NFPA formulas are actually pretty close to what we get in actual discharges. The inert agents actually run out a little bit faster than predicted, but again, with inert agents, there's a little bit of cooling, a little bit of expansion. So both of the equations tend to predict reasonably well. NFPA might be a little bit optimistic. ISO is quite conservative right now. So we're reasonably satisfied with the equations that we're using right now for agent retention. The other thing that's occurred is because we've rewritten the formulas and we take a look at the old NFPA, which would be prior to 2008, 2012, as far as hold time is concerned, we've got an example of an FM200 room at, let's say, 9.3 minutes with a peak pressure evaluation of 328 pascals. Using the new NFPA 2012 version, it would pass the hold time evaluation by about another, 10-12% or so in hold time, because the new test procedure that we have. And at the same time, if the peak pressure requirement was 250 pascals or less, it would pass that as well. So there are some advantages there. If we go down to argon or argonite, they work pretty much the same way. Notice that the hold time's gone from 7.3 minutes up to 10.3 minutes. So there's a change there of 3 minutes, which is around a 40% increase in the retention time. And we've been able to verify that these new formulas are accurate with the test regime that we went through about 4 or 5 years or so of research. So that does benefit us to some degree, particularly with inerts in North America, because it means that we have to put less effort into making the enclosure tight, and we're less likely to have to install pressure relief vents where they're not needed. And at this point, we actually know when they are needed. In this case, you'll notice in this particular examples that I've created here that that neither of these enclosures need a pressure relief vent. And not that I'm trying to sell against pressure relief vents, but it's important to know when they're needed and when they're not. And for sure, there are a lot of installations out there that do not have pressure relief vents that need them. And there's many enclosures out there that have pressure relief vents installed that don't need them. So our I guess idea is that we should be putting them in when they're needed, for sure. And that's what the evaluation can do for you. It's very simple, quick and easy to do, and it's a requirement now. So we will help you with that. So this is one of the reasons why the new test procedure will give you results that will allow you to pass hold time and also peak pressure. The previous NFPA formulas used an N value of 0.5, and we had to assume that because we're only taking a single point test at 10 pascals. Now we're taking a 2-point test at 10 and 50 pascals. It allows us to actually measure this slope, which is often 0.6, 0.7, and so on. And if that's the case, at a measurement at 10 pascals might yield a leakage area of 257 square inches. But if we have a slope of 0.71, which is not uncommon, we might have 443 square inches at 125 pascals, which is the pressure that we do our peak pressure evaluation at. So you can see by using the old test method that we don't get the advantage of the slope that might actually be occurring in the room that will allow us to pass both peak pressure and hold time evaluations. It doesn't really matter if you understand this. You put the numbers in there, you do the measurement now at 10 and 50 pascals for measuring enclosure leakage, and you automatically get that benefit. So the main change again is that in the past we would test the enclosure at 10 pascals or the maximum of the column pressure, which might be 14 or so. We just test it in both directions. Now we're testing at 10 and 50. It does require a little bit more fan power and so on, but the bonus is that it gives you longer hold times and in some cases reduces the size of the PRVs that you have to install, reduces the amount of air sealing, and the savings there could be astronomical. So this is just reiterating the same point. And the next piece, which is done reasonably frequently in North America, is to measure the lower leakage. And in this case, we have an enclosure which fails the peak pressure evaluation and hold time, and when we do a lower leakage test, it's able to pass both of them. So you can see here that that we can get better results, or we can at least see the advantage of better results by doing a lower leak test, which allows us to have more leaks at the top of the enclosure, which is good for hold time, and it's also good for peak pressure as well. So we have, in this case, a leakier enclosure, but we've been able to reduce the lower leaks down to a relatively small value of, in this case, only 6 square inches, which has allowed us to pass hold time, as you can see, of 11.1 minutes, and have almost no peak pressure whatsoever. So the lower leakage measurement is very advantageous, and the same thing can be true with Novec or inert agents as well. So we can reduce the need for pressure relief vents and get better hold times by measuring the leakage distribution. And there's two ways of doing this. One is to cover the ceiling in plastic, and I've done that I think 3 times in my life, and it takes anywhere from 2 to 6 hours depending on the size of the room to do a good job of that. That enables us to measure the size of the hole in the bottom part of the enclosure, which is where the agent leaks out. A much faster way of doing that is to use a what we call a flex duct. So one fan is ducted to the above ceiling space, the other fan measures the leakage of the room. And a new feature that we have in our new gauge, which is called a set to zero function, enables this test to be performed with one technician. We simply set the pressure across the suspended ceiling to 0 while measuring the enclosure leakage, and we get rid of the old-fashioned step that we used to have of testing the tiles with smoke to see if the smoke was going up or down. This test reduces the time it takes to do this test and reduces the technician requirement from 2 down to 1. Sometimes we'd even have 3 or 4 people doing this test. So it makes the test much easier to do. We'll be looking at a schematic of that in just a moment. And certainly if you have any questions as we're going along here, be sure and pop them into the question box, and I'll try to answer them as we go. So this is a schematic here of the lower leakage test, where we have one fan which is neutralizing the pressure across the ceiling. It's not measuring any flow. It's just acting as a neutralizing device, enabling the lower fan here to be measuring the room leakage on its own. Something that takes a little bit of practice. I've done them in as little as 20 minutes from start to finish, so they can be done relatively quickly, and again, a lot of advantages to doing that. So here we see a venting calculation done by measuring lower leaks, and we've reduced our pressure relief vent area from 137 down to 0. And there's another setup. This is one of our old systems from about 10 years ago. This is, again, this flex duct's going to the upper, to the above ceiling space, and we've got the 2 fans mounted in the same doorway. The same technique can also be used for subfloor only testing. So here we have a fan blowing in the subfloor. In this case, we would be pressurizing the room so that the pressure across what we call the walk-down floor would be 0. You notice in this picture that we have the perforated tiles covered with a grill mask material that seals them off. So this enables us to measure the below ceiling leakage area. The new ISO standard, for those of you that might be using that standard, has expanded the section on below ceiling leakage area testing and subfloor only testing. So the new version that's coming out for the ISO standard, I'm not sure when it will be released. I would think at the end of this year, maybe the beginning of next, has reinforced the section on below ceiling leakage area measurement. And in fact, the wording is in there to do it right now. It's just not as clear as it could be, but the test procedure that we have for below ceiling leakage area calculation is actually valid for ISO testing. So we do have 3 levels of training. We don't give training credits for our webinars. They're free, just information only, and we have 3 levels. The first one is for AHJs and fire protection engineers. The second is for testers, and the third is for advanced testing. And we support people that have taken our training and have got software licenses from us and so on to help us pay for our time to do that. So if you've got any questions at all about any of this, you can always send your question either to support@retrotec.com or colin@retrotec.com. I'd be happy to answer your questions. So I'm just going to jump over and take a look at, I got a couple questions in here, And we'll just discuss that for a minute, and afterwards we'll open up the software and play with it for a few minutes and see what we can see. So let's just take a look here. So someone was asking, Robert Ennis was asking, is it reasonable and acceptable to measure lower leakage area in a room that does not have a suspended ceiling but does have leakage points positioned above the required protection height? There is a thing that we can do, it's called a leak audit, where we can, let's say, measure 10 square feet of leakage, and if we can show that 9 square feet is above the ceiling, then we can say the below ceiling leakage area is 1 square foot. It's not a measurement per se, but it's an evaluation, and it falls under the engineering judgment section of NFPA, which does allow you to do that. A lot of the authorities are antsy about accepting something you didn't actually measure, but in a lot of cases, if they know what they're doing and they understand how the standard works and so on, they can accept this. There is a limit to how much upper leakage we should have, and in most jurisdictions, installations are being done where they're putting in slab-to-slab walls around the enclosure, which is much preferable. That usually allows us to do a below-ceiling leakage area measurement if there's a suspended ceiling, which is a convenient separation between upper and lower. The other way to do that is if there's a false floor, we can actually measure the leakage below the false floor and then more accurately make statements about where the rest of the leakage is. So for example, again, if we have 10 square feet of leakage and we do a subfloor only test and we discover there's only half a square foot of leakage below the subfloor, virtually no leakage in the walls that you can see, if they're carefully inspected, then we could actually use that as evidence that we have a leakage split that is 9.5 square feet of upper leaks and 0.5 square feet of lower leaks, and that can be put into our software, and we'll do a calculation of the new retention time, which will be roughly about 5 times longer than it was before. So someone was asking, if we're not using a second blower, can we choose to use sealant for the ceiling panel instead of plastic on the ceiling? I think what you're saying is, can you actually seal the tiles in place? It's actually relatively difficult to do. It is possible to caulk every tile in place, but if they're not well sealed, that little itty-bitty crack around the tile is enough to make the enclosure fail. But you could theoretically caulk every tile to the suspended ceiling and actually seal the ceiling in place. That would be possible. Someone was asking about the door fan test is only once. In fact, both the ISO and NFPA standards require an evaluation to be done, I believe, on an annual basis, and if any doubt exists, the door fan test has to be repeated. I know in some jurisdictions this is not done, but in Korea, for example, they do repeat the test every year. And in other jurisdictions, depending on the authorities, they may require a repeat test every year, at least an evaluation done to see if any changes have been made to the enclosure, a visual inspection, and as the standard says, quote, if any doubt exists, then the test has to be repeated. So there is a requirement to do an evaluation of the enclosure every year, and it's something that can be done when the annual inspection is done. So a person was asking where the best place for the PRV. The pressure relief vents, or PRVs, are best installed as high up as possible. The reason for that is when the agent is being discharged, and if there is any pressure in the room, it will tend to force air out of the vents and not agent. So that tends to work quite well. The other thing is that they won't add to agent loss when you're in the hold time phase. The downside is if they're installed above a suspended ceiling, the suspended ceiling has to have sufficient vent area in it in order that when the system discharges, that the agent on its way to the pressure relief vent doesn't take the suspended ceiling with it. And there's a fairly easy way to evaluate the pressure that will occur across the suspended ceiling. For typical lightweight suspended ceilings, they don't really handle much more than about 50 pascals well. So that means that the area in the suspended ceiling has to be roughly about 5 times what the area of the pressure relief vent is. So you would have to have several perforated tiles or egg crate grills in the suspended ceiling to allow the pressure to vent past the suspended ceiling and through the pressure relief vents. The other option would be to install the pressure relief vents right at the top of the wall right next to the suspended ceiling. If you are discharging agent only below the suspended ceiling, it's not a bad situation, but in general, getting them up as high as possible is best. So someone was asking, can we install it on the raised floor? I'm not sure if you're asking, can we install the PRVs on the raised floor? I wouldn't suggest that. There probably is not enough pressure in order to open the PRV. The PRVs usually open at around 50 to 80 pascals, and the column pressure of the agent is usually around, for inerts, is around 1 or 2 pascals. For halocarbons, just maybe 4 or 5 or 10 pascals at the most. So chances are they won't open up in the false floor, but there is a bit of leakage around the vanes of the PRV, so it's not the best place to install them, but theoretically there's no reason to not install them in the raised floor. They could work. So someone was asking is, should the PRV be specified before the test so it can be installed and included in the test? Well, one of the reasons for the designer calculator is to figure out whether we have the potential of needing a PRV in the first place. If you're showing up as a tester and there's no PRV installed and they want occupancy next week, then it's a little bit late to start to worry about putting a PRV in there. Really needs to be considered during the design phase and be part of the plans. So Nevid is saying when we're discharging gas in a room, it seems we always have a positive pressure. That is true for an inert. We will always have positive pressure spikes with inerts, for sure. There's no negative pressure spike whatsoever with all inert agents, except maybe CO2, particularly if we're using liquid CO2. We can have a pretty powerful negative pressure spike. With compressed CO2, typically not. It works pretty much the way inerts do, but with the halocarbons, most of the halocarbons produce a larger negative spike than a positive spike, particularly in drier climates, say humidity's under 40%. So someone was asking if the vent is normally closed, in the event of an alarm, is it require to open the damper for a few seconds and close before the FM200 discharge? One of the things that we can do with vent closure timing, particularly if we have vents that are isolating the HVAC system, is to delay the closing of the pressure relief vents until the agent is discharged. There's very little increased losses due to the extra area of the vents that are open. So if we can have those vents closed at the end of the agent discharge instead of at the beginning, then we get kind of a free venting, so to speak, there was a thought that we have to close all events at discharge, but it's really during the hold time. There's not much agent lost during the discharge. Even a 60-second inert agent discharge, there's not that much agent lost during that period. So closing the vents is not as important as you might think it is. But certainly closing it during the hold time is important. I'm not sure if that answers your question or not. Okay, so that seems to be all the questions that we have for now. So I'm just going to jump over to our software for a moment and just take a look. We've already looked at the enclosure design section. So the next part that you would open up would be the section for putting in information about the test technician, your company name, and so on. Once you do a test and you save this information, you can just do a save as when you do a new test and save all that information, and so you don't have to re-enter it. All of the files, incidentally, are kept in date stamped order, so it's year, month, day, hour, minute. So all your tests will be saved in a folder that, in my case, is on my C drive under, let's see if I can find out where that is. There we go. So I just click under Documents, Retrotec, and all the tests that I've done are all there. And you can see it starts with the type of test, NFPA, year, month, day, hour, minute. So they all get listed in that order. You can rename them if you want to, for sure. So those are the actual tests, which is the test data. When we ask for reports, the reports come out in Word or Excel, depending on what you choose, and they come out in the same format of NFPA test, and then year, month, day, hour, minute, and so on. And also you'll find in there the templates that are used, and if you open up the template, let's just take a quick look at the template. Whenever you do an NFPA template, in this case in English, it will be in this format, and if you actually do a test report, it'll make more sense. And these funny things here are the data fields that are pulled in from the software. So you can take this template and change this with your test company logo and various things. So every time you do a test, all this basic information is in there. And a very cool thing that we've done on this particular report format is we've done all the work necessary in order to do 90% of the reporting requirement. So it gives you a nice summary of hold time. It goes through all of the statements about peak pressure compliance, assumptions and warnings, background for the test, and so on. The stuff that is not looked at all that much, but all the documentation is all there. You can see it's quite extensive. And it's pretty much everything that we put into a report is taken care of using the report template. You can make multiple report templates and put them in other folders, and whichever template is in that particular folder that you found it in the first place is the one that Fantastic Integrity goes to in order to do your next test. So I'll just do a report for you and show you very quickly how that works. So in this case, let's say that we're going to open a test. So we go back to all these tests that we've done before, and I don't even know how much data there will be in these tests, but let's just open this one from here. So we've now populated the software with this test data. As you can see, there's not much in here. Witness company name. And then when we go to, we just save that, and then we can go over here which says generate reports. Now I think we've added a new feature on here which allows you to generate reports from down here, because I don't think that people realize that they could generate reports from the software. the report generation is really what you're licensed to use. You can still use the software without report generation, but report generation is really the meat and bones of the software that we provide. Whenever we do a test, I would say it saves us 2 or 3 hours per test just to use the report generator. So once we've done all this work, we simply go to generate report. And the software and the report templates can also be upgraded online. It will ask you if you want to upgrade them. At that point, it will upgrade them. And if you've made changes to it, you can take your particular version that you've updated with your logos, this and that, and put them in another folder temporarily, and then take a look at the upgraded version and see whether you like it. So that's all that's required. You notice we've got a few blanks here because we haven't filled in the data, but we've gone from a template now to a finished report. So we have a cover page that you can again put your logo on and your name, rank, and serial number, and so on. The summary report and all the text that we need for the assumptions, warning, background, discussion of the results, the data that you took during the test, the results of the test, the peak pressure test. This is what your data looks like, and the calibration certificate for your particular fan that you used, and serial number, and so on. Here's the negative peak pressure results, and it's all in there. So let's see if we've got any questions about that. So someone was asking, do we have extra liability if we use calculations for peak pressure that are not actually included in NFPA 2012? NFPA 2012 doesn't actually provide peak pressure formulas. It says you must do a peak pressure evaluation and leaves it up to you as to how you do that peak pressure evaluation. So there are various sources of peak pressure formulas. One is the manufacturer, and the other one is FSSA, which is data that's been publicly available and so on. It's probably the best data that's out there, and it's been well vetted and looked at by all the major companies in the industry. So I would say that it's about as good as it gets in terms of peak pressure evaluation. So as far as liability is concerned, it seems like there's a lot of liability that's being incurred already by virtue of the fact that no peak pressure evaluation whatsoever is being done. So what the liability is of using certain formulas, I really have no idea. Actually, somebody did ask a very important question about mixing and no mixing. When we're using the enclosure design or the venting calculator, there's a calculation in there for mixing and no mixing, and it's really important that we take a look at that. In cases where we have a high minimum protected height, descending interface will always produce a relatively short hold time, and often the only way to get around that is to use continuum mixing. So with continuum mixing, we can put in extra agent, we can increase our hold time relatively easily, and we can provide protection for the complete enclosure. So that is one of the fundamental pieces that is always, just about always missed in enclosure integrity or an enclosure design, is that it is always assumed that it's descending interface, and it's often not the case. I would say that almost half of all enclosures actually have continuum mixing. And most of the standards say that if doubt exists, you should do an evaluation of continuum mixing and descending interface as well. So the data that we need to enter for continuum mixing, let's just close this down. We'll collapse this. Let's just jump over to building and Enclosure details. We'll collapse these other windows here so you can just see one at a time. So we only have the building and extinguishing details. So in this case, we have descending interface. When we have descending interface, it asks for the required protected height, HP in this case. We've got this in metric, but it all works the same way. When we go to continuous mixing, we're now asked to specify the minimum concentration. The required protected height is still there, but it's not actually used in the evaluation. So whenever you make the right choices in the software, in this case calculate hold time result using continuous mixing, descending interface, or extended discharge, it will ask you a different series of questions and use different numbers in order to make those evaluations. One really important value that we have to put in here is to make sure that our initial concentration, let's just put the right amount of agent in here. Let's see, let's put in, what do we have as, we've got a Caro, okay, so we want to have a design, let's say, of 8%. And so in this case, we have too much agent in here. We've got 80 kilograms of agent. It's going to provide an initial concentration of 10.8% roughly. Our design concentration is 8%, and we actually have to hold 85% of 8% at the end of 10 minutes. So even though this doesn't look right, this would be the proper way of handling the concentrations, so that we can't confuse initial concentration with design. So initial concentration should be at design or above design. And if it's above design, then we still have to hold 85% of design, not 85% of initial. Okay, so I'm just reading the other questions that people have here. So Dean was asking what would typically cause a room to pass negative pressure with FM200 but fail positive? FM200 will, at around our 40% humidity, have roughly the same positive and negative peak pressure spike. So in order to pass negative and fail positive, we'd have to have a fairly high humidity, which would make it easy to pass negative, because with high humidities we have relatively small negative pressure spikes. We do have to, however, when we go to the venting analysis, have to put in the humidity range. Let's see if I can find the right spot. Here we go. Minimum humidity 30%, maximum humidity 60%. So there has to be a range in there of humidities that we have to cover. So it would be unusual for a room to only exist in high humidity. Usually there'd be a range from min-max, and they would be your design minimum, which would be the humidity that the room is likely to not fall below, I think, 95% of the time, and the upper one is the highest humidity that you would expect 95% of the time as well. That may actually be kind of a hard value to figure out, but humidity meters can be relatively inexpensive. You can get one for about 25 bucks or so. So, you know, when you're going from installation to installation, you can just kind of have it with you and just get a sense for the humidities that different enclosures would be run at. And sometimes there will actually be a design specification for a computer room that they will be maintaining humidities within a narrow range. So it's up to you to find out what that range is. So Evan was asking about articles about requiring us to shut down HVAC before release so that mixing does not occur. Well, now there's a difference between mixing and building HVAC. So if the building HVAC is on, for example, then we have a supply and we have a return. So as the agent is discharged, it's sucked up by the return and the supply is putting fresh air into the enclosure. So that's quite different from, let's say, having a dedicated HVAC system that's merely circulating air within an enclosure and just mixing it around. So the HVAC, building HVAC, will actually suck the agent out and blow air into the enclosure. And in that case, the HVAC needs to be shut down. A recirculating HVAC is quite different, and it's quite common to have a Liebert-style unit, which is blowing air-conditioned air into the subfloor, blowing back up into the room, and it's circulating around. That will cause continuous mixing. Building HVAC will just cause continuous agent loss, which is quite different from mixing. So someone was asking, the initial concentration was a little bit lower than the design. If the initial concentration is lower than design, then there needs to be more agent in there, unfortunately. That it's a requirement that you have at least the design concentration in the enclosure. So, someone was saying that most air conditioning units are recirculating air in the inside. That is true. We also, if we are doing a test and we have a situation where the dedicated HVAC is going to be running inside the enclosure and blowing air from the room into the subfloor, the pressure in that subfloor will often be 25, 50, 100 pascals or whatever. That has to be entered into the software as a pressure that will be there during the hold time. And let's see if I can find out where that is. Bias pressure during the fan test, which is during when the door fan test is being done, but there's another one that is a pressure that will occur during, here it is, bias pressure during the hold time. So if, for example, we have a 25 pascal pressure in the subfloor, this 25 pascal pressure must be entered here, and let's say it's 25 pascals, and that will add to the pressure that's pushing the agent out of the room. In fact, it will reduce the hold time dramatically. So someone else is asking, in the case of nozzles that are lower than the minimum protected height, how can we pass the test? Even if the nozzles are relatively low down, they will flood the room above them. Nozzles are usually put in at the upper part of the room, but even if you had nozzles halfway down the room and you discharge them, they would definitely flood the room with agent. Okay, so I think that pretty well takes care of everything for today. We're just past our 1 hour timeline, and certainly if you have any questions, we'd be happy to answer them if you just send us an email. And thank you very much for your attention. And I'll stay online a little bit longer to answer some other questions. I might answer some of them by email. But thank you very much for your attention, and